Okay, welcome back dear students to the tutorial about the chemical applications of group theory, and this is the fourth video in this series. We have been discussing about the application of group theory in spectroscopy, especially in the last two videos we were discussed about what are the conditions for Raman active and IR active vibrations. And these were our conclusions. A fundamental vibration, a fundamental transition will be Raman active if the normal mode belongs to same representation as any one of the binary products of the Cartesian coordinates. That means for a fundamental mode or normal mode to be Raman active, its symmetry should be same as any one of the binary products of Cartesian coordinates, that is x square, y square, x square, y square, xz, yz, xy, etc. And for a vibrational mode or normal mode to be IR active, the normal mode belongs to the same representation as any one of the Cartesian coordinates. For example, in C2V, A1 mode belongs to Z coordinate, or its basis is Z, so it is IR active, and X belongs to B1, B1 is IR active, and Y belongs to B2, B2 is IR active. A2, none of the coordinate belongs to the A2 mode, therefore A2 is IR inactive. And in the case of Raman, this all modes belongs to any one of these binary products. Therefore, all the modes in C2V point group are Raman active. And these were our conclusion. Now, in this video, we are going to discuss about the prediction of IR and Raman active fundamental modes or normal modes of NH3. In the last video, we were discussed about the water molecule as example. In this video, we are taking ammonia molecule as example. Ammonia, we know that is a non-linear molecule, is a pyramidal molecule, and there are 4 atoms. Okay, therefore, normal modes of vibration is equal to 3n minus 6, that is 3 into 4, 12 minus 6 is equal to 12. There are 12 normal modes of vibration. And the first step to find out the vibrational modes, symmetry of the vibrational modes, is to calculate the total character, calculation of total character. And for that, we are fixing XYZ Cartesian coordinate vectors to all the atoms. There are 4 atoms here. In an ammonia molecule, there are 4 atoms. We are fixing XYZ coordinate in all the atoms. XYZ coordinate is fixing in all the atoms. Therefore, there are 12 vectors. Okay, and this was our equation to calculate the character of the operation, symmetry operation, that is NR into plus or minus 1 plus 2 cos theta. I think you might have remembered this equation. In the last video, we were discussed about this. That is, the character of the symmetry operation is equal to NR, where NR is the number of atoms unshifted during the operation, during the symmetry operation, and theta is the angle of rotation. In this equation, in this method, we are considered all the operation either a proper rotation or an improper rotation. Okay, if you forget this, please watch the last videos. I had uploaded. Okay, anyway, in this case, first we discuss identity operation. And during identity operation, all the 4 atoms are unchanged in position because identity is doing nothing. Therefore, here NR is equal to, N is equal to 4. 4 into 1 plus 2 cos theta is equal to 0 here. Therefore, cos 0 is equal to 1. So, 2 into 1 plus 2 into 1 plus 3, 3 into 4 is equal to 12. So the character of chi E, character of identity operation is equal to 12. Okay. Okay, next is C3 axis, character of C3 axis. And C3 axis, we know that in ammonia molecule, C3 axis passes through the nitrogen and none of this hydrogen atom, or in between this hydrogen atom, passing through only through the nitrogen. Therefore, nitrogen is fixed in position and all the hydrogens changes their position. Okay. Therefore, N, number of atoms unshifted, is equal to 1. And here theta is equal to 120 degree. So chi C3, character of C3 is equal to N C3 into 1 plus 2 cos theta, because it is a proper rotation, therefore plus sign here. Okay. So N is equal to, there is a mistake here, that N is equal to 1. Okay. So 1 into 1 plus 2 cos 120, theta is equal to 120. And cos 120 is equal to minus sin 30. Okay. Cos 120 is equal to minus sin 30. So we can write 1 into 1 minus 2 sin 30. That is 1 minus 2 into sin 30 is equal to 1 by 2. That is 1 minus 1 is equal to 0. So character of C3 operation is equal to 0. Or another way, cos 120 is equal to minus half. Cos 120 is equal to minus half. Minus half into 2 is equal to minus 1. 1 minus 1 is equal to 0. Okay, is equal to 0. Okay, next vertical plane. Character of C3, 0. Character of E, we got 12. For C3, it is 0. And vertical plane. There are three vertical plane, identical vertical. There are three equivalent vertical planes passing through nitrogen. Okay, and any one of the hydrogen. That is, this is one vertical plane, and this is another vertical plane, and this is another vertical plane. And these all vertical planes are identical and all pass through one nitrogen and one hydrogen. Therefore, number of atoms unshifted is equal to 2. Number of atoms unshifted is equal to 2. And therefore, N sigma V is equal to 2. And reflection can be treated as an improper rotation. That means sigma V can be written as C1 into sigma V. C1 is equal to E, multiplying with E, no change, therefore C1 into sigma V, and that is equal to S1. So sigma V considered as an improper rotation of order 1. Therefore theta is equal to 0. So N sigma V is equal to, chi sigma V, character of sigma V is equal to N sigma V into 2 cos theta minus 1. This equation is actually 2 cos theta minus 1, or minus 1 plus cos theta, and that is equal to 2 into cos theta, here cos 0 is equal to 1. 1, okay, this equation is actually 2 into 2 cos 0 minus 1, and that is equal to 2 into 2 plus 2 into cos 0 is equal to 1 minus 1, and 2 minus 1 is equal to 1, 1 into 2 is equal to 2, that is we get 2 here. Okay, and that is the character of vertical plane. 3 sigma V planes are 2. So we got character of E is equal to 12, character of C3 is equal to 0, character of sigma V is equal to 2. C3 and C32 together, 2C3, we are writing it is a class. Together C3 and C32 form a class. So 2C3, 3 sigma V, another class. Okay, there are 3 classes in C3V point group. NH3 belongs to C3V point group, isn't it? Okay, NH3 is a molecule belongs to C3V point group. There are 3 classes E, 2C3 and 3 sigma V. And so total character, gamma total is equal to 12, 0, 2. Character of E is equal to 12, character of C3 is equal to 0, character of sigma V is equal to 2. And this is a reducible representation. And we want to reduce this total representation, which is a reducible representation, into irreducible representation using the character. This is the character table of C3V. So our reduction formula, I think you remember, that is N R is equal to 1 by H into Gi into chi r into chi I r. Okay, this was our reduction formula. That is number of times the n chi I is equal to. Okay, number of times an irreducible representation present in the reducible representation is equal to 1 by h. H is the order into gi. Gi is the number of elements in the class into chi r, character of the reducible representation, into chi ir, character of the irreducible representation. Therefore, na1 is equal to 1 by 6 because character of C3b is equal to, order of C3b is equal to 6 into 1 into number of elements in this class is 1. 1 into character of reducible representation 12 into E 1, 12 into 1. Plus this is 0, C3 here 0, 0 multiplied 1 is equal to 0. And here 3 into 2 into 1, 3 into 2 into 1, 3 into 2 into 1. And that is 12 plus 2 into 3 6, 18 by 6 is equal to 3. Therefore A1 3 times present in this reducible representation. And Na2 is equal to 1 by 6 into 1 into 12 into 1, 1 into 12 into 1. And next 0. Next 2 into 3 into 2 into minus 1, 3 into 2 into minus 1, 3 into 2 into minus 1. Okay, and this is minus 6, 12 minus 6 is equal to 6, 6 by 6 is equal to 1. Therefore, A2 present only 1 times in this reducible representation. And NE is equal to 1 into 12 into 2, 1 into 12 into 2. Here 0 minus 1 0, 2 into 0 0. Okay, so it is 24, 24 by 6 is equal to 4. Therefore, E appears 4 times. Therefore, the total character is 3A1 plus A2 plus 4E. 3A1 plus 1A2 plus 4E. And that is the 12 degrees of freedom. We know that there are 3n total degrees of freedom. This total representation include all the degrees of freedom. This total representation include all the 3n degrees of freedom. Here 3n means 3 into 4 and that is equal to 12 degrees of freedom. That include both translational, rotational and vibration degrees of freedom, and that is 3A1 plus A2 plus 4E. Here how it becomes 12? 3 plus 1 is equal to 4, 4 plus 4, 8 only now. But you remember that here E is a two-dimensional representation. Okay, because we know that A is the one-dimensional representation. E, the character, E, the letter E represents a two-dimensional representation. Therefore, E represents two motion. Okay, so 4 into 2, 8. 8 plus 1, 9. 9 into 3, 12. Total 12 degrees of freedom. Okay, clear? That is in 4E, actually there are 4 into 2, 8 degrees of freedom because E is a two-dimensional representation. 1E represents two motion. Okay, 8 plus 1, 9 into 3 is equal to 12. There are 12 degrees of freedom. And what was the next step? That is, now we determined the total representation. From the total representation on reduction, we get the all the degrees of freedom, which include rotational, translational and vibration degrees of freedom. Now our next step is to subtract the translation degrees of freedom and rotational degrees of freedom. And look at the character table, and our total representation is this. Gamma total is equal to 3A1 plus A2 plus 4E. That is a total representation. And translational degrees of freedom. Look here. Translation degrees of freedom, Z is a translation in the Z direction, that is A1, and translation in X and Y direction is E. Therefore, gamma translation is A1 plus E. And rotation in Z direction is A2. Rotation in X and Y direction is E. Therefore, A2 plus E. So, gamma rotation is equal to A2 plus E. And subtract this gamma translation and gamma rotation from gamma total. We get 3A1 minus A1 is equal to 2A1. And A2 minus A2, that is cancelled. 4E minus E, that is 2E cancelled, then 2E. And that is 2A1 plus 2E, that is the vibrational symmetries of 6 vibration normal modes of vibration. How it becomes 6? 2A1. 2A1, that is 2 modes of vibration, and 2E. I already told you that E is a two-dimensional representation. So E represents 2 modes. 1E represents 2 modes of vibration. So 2E represents 4 modes of vibration. 4 into 2, 6. Therefore, our vibrational symmetries of the vibration, gamma vibration, is equal to 2A1 plus 2E. Okay, 2E include 4 vibration, 2A1, 2 vibration, 4 plus 2, 6 vibration. Okay. Okay, so our vibrational degrees of freedoms of water ammonia molecule, NH3 molecule, is 2A1, having symmetry 2A1, 2E. That is the symmetries of the vibrational modes. Now our discussion is, which of these modes are IR and Raman active? Okay, first we are discussing IR and Raman activity of A1 mode. There are two A1 modes here. And in the last video, we had studied that a normal mode is IR active if the mode has same symmetry as any one of the dipole vectors x, y or z. Okay. Okay, a normal mode is IR active if the mode has same symmetry as any one of the dipole vectors x, y or z. Now A is here. Okay, look here in the character table. A is here. A1 is here. A1 transforms as Z, or Z transforms as A1, or the basic function of A1 is Z. Okay, this is a Cartesian coordinate. Therefore, Z belongs to A1. Therefore, A1 is IR active. Okay, Z vector belongs to A1 mode. This mode is IR active. How we have explained this in the last video? We are discussed it very detailed. That is, probability in the z direction is equal to integral minus infinity to plus infinity psi I z psi f d2. Psi I told you that in the last video, that is all symmetries of ground vibration level of all mode is A1. So psi I is A1, and Z is here A1, Z is A1, and psi f, we know that psi f is the first excited state, vibration always from 0th level to first level, that is a highest intensity vibration, and symmetry of the first level is the symmetry of the mode itself, because here mode is A1, so A1 raised to 1 is equal to A1 itself, so it is A1. So A1 into A1 into A1 is equal to A1. So integral of A1 is not equal to 0. Therefore, this mode is IR active. Okay. Next, Raman activity of A1 mode. A1 mode is IR active. Now we are discussing Raman activity of A1 mode. A mode will be Raman active if its symmetry is same as any one of the binary products x square, y square, z square, xy, xz or yz. And this was we had studied in the last video. That is a vibration or normal mode to be Raman active. The symmetry of the mode should be any one of the binary products, that is x square, y square, z square, xy, xz and yz. And look at the character table. A1 is here. Okay, look at the area 4. Here z square and a linear combination of x square and y square, that is x square plus y square, belongs to A1. Okay, therefore A1 mode will be Raman active. A1 mode will be Raman active. Okay. Okay, finally, the IR and Raman activity of E mode. That is the vibrations of ammonia molecules are 2A1 plus 2E. Okay, A1 mode is IR and Raman active. Now we are going to discuss about the IR and Raman activity of E mode of vibration. And look at the character table. Here E is here, and X and Y, the dipole vectors, dipole moment vectors X and Y transforms as E. Therefore, E is IR active. And the binary products XY, XZ and YZ, and their linear combination x square minus pi square also transforms as E, therefore it is also Raman active. Therefore vibration is Raman active and IR active, both IR and Raman active. So all these two modes, all the 6 modes, 2A1 and 4E modes are all Raman active and IR active. Okay, read well, please do more examples, okay, and study thoroughly. Okay, thank you.